Our team is composed of Junhyuk Lee, Junwon Lee, Kyuju, and today we will present about the result of pressure sensor manufacturing. This is a picture of each thickness of the sensor and diaphragm we designed. Next is the mask design that we made. The picture below is the mask design that was designed using a 2D program. The picture above is the result of making the design into a real film mask. You can see how the real mask was implemented. Before fabricating the pressure sensor, we used Komoso to simulate the force on the membrane of the film mask. This allowed us to calculate the average strain, maximum stress, and pressure values. You can find the results on this page. This page shows the calculated strain on the pressure sensor. For two main variables, we calculated the strain on R1 as 1.89 and R2 as minus 2.08. These values will play an important role in the subsequent process. The following table calculates the output voltage change according to the strain. We have calculated how the output voltage will change according to the strain when a 5 voltage is applied, which can be found in this table. When the actual sensor is completed in the future, we plan to compare the measured data with theoretical values. This page is a checklist for the all of fabrication process that we are currently working on. We have written down the solutions, method, and process step we are using in detail. This allows us to carefully check each step and proceed. Based on this checklist mentioned earlier, we have visualized the main points at each stage in 3D modeling. We will then show you the front and back side of the finally manufactured sensor. First, I will explain the process flowchart to adjust silicon-based supports and diaphragm thickness. 300 nanometer of silicon oxide was deposited with primary thermal oxidation, which serves as a protective layer in TMAH solutions. After that, we created the open window mask through the photorisography process, and we were able to obtain the targeted value as a result of measuring the corner compensation. The silicon oxide layer was etched for 4 minutes using BOE, and it was completed neatly without over-etching. Silicon was etched with TMAH solution and etched for 1 hour after confirming that the actual etch rate was 0.5 micrometer per minute through the piece wafer. Subsequently, silicon oxide was deposited at 300 nanometer to protect the back etching and served as the front insulating layer, and chrome was deposited at 200 nanometer on top of it, followed by metal mask patterning. As a result of patterning, we were able to confirm that it came out successfully as we designed it. After etching the chrome and removing the PR, we confirmed that it was completed as designed. As a result of individual resistance measurements, the average values were 117 and 123 respectively. Finally, we conducted backside etching mask patterning, and after that, the silicon oxide layer was etched with BOE, but it is believed that over-etching occurred due to weak adhesion between PR and oxide layer. The wafer's thickness was about 515 micrometer, and the target etching thickness was set to 481 micrometer. The etching was planned for 16 hours by calculating the average etching rate as 0.5 micrometer per minute, but after 11 and a half hours, the actual etching thickness was only 294 micrometer. Accordingly, it was decided to perform etching for an additional 7.2 hours after recalculating the etching rate, but after 5 hours, all the samples were separated and it was confirmed that some films were excessively etched, so the work was stopped. Finally, the remaining film thickness was measured as 65 micrometer. When we started to measure the performance of samples with the wireless system, we first measured the displacement change of the sample. We used a syringe pump to provide different air pressure to the sample, causing the film to produce different displacement and deformations, and recorded the data using a laser vibrometer. We first measured our own sample and obtained the data shown in the figure. Although our film thickness is about 65 microns due to the large size of our film, it can still produce a displacement of more than 30 microns under high air pressure. However, due to the poor performance of the sensor part, we cannot get a very clear output voltage signal. Therefore, we used other samples that have been proven to be useful for the next measurement, and the displacement under different air pressure is shown in the figure. In order to verify that the data we expect to test through the HX711 based wireless system is reliable, we first use the existing AD620 amplifier to measure the output voltage signal of the sample through DAQ data transmission. The data obtained can be used to verify the reliability of the data measured using a wireless system. Next, we use Arduino IDE to record data with PyCharm and ran a web page displaying real-time graph. Since then, we have tested whether the data measured through the sensor is recorded normally and displayed in real time on the graph. As a result, it was confirmed that data, measurement, recording, and visualization all worked correctly. Let me explain the process of storing and visualizing the data. Using the PyCharm program, the data received from ESP32 was saved as an Excel file. The stored data can be used for subsequent analysis and was used to create the final graph. This is a wireless connection testing process. The wire that supplied the current to the ESP32 was always connected to the measuring laptop. To address this, we connected our ESP32 to another laptop and confirmed that the data is actually being sent wirelessly. The video on the right shows final measurement video. Data can be collected 5 times per second, and it was measured by increasing the pressure from 0 to 517 mmHg. The stored data can be managed in Excel, and changes in data can be intuitively identified through real-time graph. This is a comparison of the wireless connection results, the data measured using HX711 on the left, and the data measured using AD620 on the right. Because the gain value is different, the data measured with AD620 is higher, but it can be seen that it is almost the same value when calculating the two inversely, which means that the data measured with HX711 came out well. Comparing the measured displacement with the design displacement and the output voltage values according to the pressure change, the values shown in the final test were very similar to the initial simulation results. When designing a sensor, the offset should be considered to prevent measurement error. The photoresorption process should prevent damage to the photoresist protective layer, and the TMAH etching should control the time and thickness accurately. Incomplete photoresist protection can lead to unintended etching, and two-way etching can lead to sample thickness being out of prediction. Finally, sufficient testing is needed to increase the voltage of the Wheatstone bridge to improve the output voltage and to reduce measurement accuracy and noise. In conclusion, detailed management of the process and thorough testing lead to optimal results. Thank you for your attention.